Hey, non-AP physics class. Jesse here. Now what is a fidget spinner? Well, a fidget spinner is a toy invented for stress relief and maybe helps people who have fidgeting problems focus a little more when they're distracted. It was invented in the 1990s and repopularized in 2017 because of things like memes or something. And you may ask, why did Jesse tell me all this stuff? Well, Mr. Delorier did tell me the video has to be 10 minutes long, so there it is. Now, let's get to the physics of it. So, at the center of every single fidget spinner, there is something called a ball bearing. And if you don't know what a ball bearing is, then today is your lucky day because I'll be explaining it to you. So if you take the fidget spinner apart with these two pieces, you can actually see the ball bearing. Alright? I cannot show it to you too close because my camera can't focus that close, but you get the idea. Alright? So in a ball bearing, there is composed of two different races. There's one inner race of this smaller one right here on the inside, and there's one outer race on the outside. All right, and in between the two races, there are little balls in between. So when one of these races is stationary and the other one is spinning, then the balls are able to spin. And this little mechanism is the main driving force to keep the friction at a minimum. Instead of, let's say, a pencil in a socket and just spinning around, that produces a lot of friction. So these balls really help in reducing the amount of friction generated from spinning. All right. And there's many different applications to this little device called the ball bearing other than fidget spinners. Yeah. So I have a skateboard wheel over here. You see this little skateboard. So there's actually two ball bearings on a skateboard wheel, one on each side. And these just help reduce friction when you're rolling. So to keep the wheel spinning and to keep efficiency when you're pushing the skateboard. And also, got my hands a little dirty, we have this yo-yo. And there's a little tiny itty bitty ball bearing in the yo-yo. Let's take it apart and see. And it's a very, very small ball bearing. As you can see here, it's a tiny little bitty ball bearing. But this is pretty much the main price point of the yo-yo, because the better the ball bearing is in a yo-yo, the faster it could spin and the longer it could spin. And of course, it is a lot more expensive when your ball bearing can spin faster and longer. All right. Okay, I'll just leave this here. And other than like toys and skateboards and all that other stuff, it is also used in cars, also used in bikes, and like airplanes and all that stuff, because the reduced amount of friction really helps, again, keeping the efficiency of the contraptions, and yeah, that's it. Alright, so now we're done with the ball bearing aspect of the fidget spinner. So the next question is, why is a fidget spinner symmetrical? Why is there, like, on this specific spinner, there's like three little prongs that go onto the side that are separated by 60 degrees, which keep it symmetrical and keep it spinning? Alright? So with this question, let's bring it all the way back to when we did Newton's second law, which is F equals ma. And we also use the other equation, the centripetal acceleration equation, which is a equals b squared over r. Alright, so if we combine these two equations, we get Fc equals mv squared over r. So this is the centripetal acceleration, no, centripetal force equation. All right, the centripetal force equation. So the reason why it relates to this is from the diagrams. All right, so normal diagram is axes right here somewhere, a little string attached to the axes, and a random mass attached to the string. So if the mass is rotating clockwise, then the velocity would be this way also. Then the mass will be moving this way, which is the velocity. And at that point, the velocity is parallel to the ground. And because of this, the force vector shoots up the string from the mass all the way to the axes. Alright? So, this is the centripetal of force equation. How do you apply this to the diagram? Well, V, velocity of the object. Pretty straightforward. R, the length of the string. Easy. M, the mass of the object. Alright? And of course, where does F go? F goes up the string. It shoots up the string. Alright? Easy. So this diagram can be really easily demonstrated through the yo-yo trick which is called around the world. Alright? Where you just swing the yo-yo around like a crazy lunatic and hope you don't hit anything. And I'm gonna show you guys how it works. Alright? Alright, so this is the around the world yo-yo trick. As you can see, you start at a neutral position, and you just let go of the yo-yo as you swing your hands in a little circle. So then the yo-yo can make all the way around in a 360-degree motion. Alright? So, how this relates to the diagram of centripetal force is you pretend my fingers are the axes. Of course, the string is the string, and the actual yo-yo is the mass represented. Okay? And how the actual force is being applied is that since the force is shooting up the string from the mass, my fingers are actually being pulled. Alright? So if you freeze the frame right here, when the mass is at the top, the mass is actually pulling the string up from my finger, so then I can feel a little tug up when the mass is at the very top. And of course, when the mass is at the bottom, I can feel my fingers pull down and each side gets pulled to each side. And yeah, that's just the demonstration for centripetal force of one mass. But this little diagram over here, the first diagram that we drew, this isn't the proper way to demonstrate the physics behind a fidget spinner. The physics behind how the fidget spinner keeps on spinning. Alright? The proper way to draw the diagram for the fidget spinner is to add 3 more masses onto the diagram. Alright? Like the 3 little spokes on this fidget spinner. So you have to add 3 more little masses from the axes in order to properly demonstrate the diagram, alright? Diagram of a fidget spinner, of course. So, you have the normal diagram, and then you add 2 more strings and 2 more masses. And they're all spinning in the same direction, clockwise, let's say. Alright, so this is the proper representation of this fidget spinner. So, why is the first one so different than the second one? So, if you want to demonstrate the first one in the fidget spinner, then let's take out these masses over here. You see these 2 little masses over here, which leaves this fidget spinner to have only one little mass, one little weight, with 2 empty holes. And what happens if you try to spin this? It just like wobbles a lot, and it can't keep its balance properly. I can't even hold this. So this one mass, if there's only one mass, then it just gets out of control. So this is the demonstration for the first diagram. All right, this is the first diagram demonstration. So if we add the two other masses, then it spins properly. All right, so why is that? So if you look at the first diagram, the net force at any given moment is in the same direction as the force of tension. All right, so if the object is at the bottom, let's say, then it gets pulled down, just like I showed in the Round the World yo-yo trick. All right, it gets pulled in a different direction all the time, and the force is directed that way. But in the second diagram, it's really different because there's two extra forces acting to counter the first one. All right, so these two extra forces actually cause the object, the net force of the object, of the axes, to remain at 0. And this is really important because this keeps the fidget spinner still. It keeps it still, alright? So this stillness, this net force, which equals to 0, actually keeps the object from spinning out of control. It keeps it in your hand even when you put on one finger, alright? It keeps it on your hand if you just put on one finger. Alright? So that's why the net force has to equal 0 for it to spin on your finger and not like jiggle around or anything and jerk around. To just keep it on your finger. Okay? So of course, let's bring it back to the yo-yo. So the yo-yo is circular, so then all the weight is distributed evenly around the axes. So that means that the net force equals to 0, which means that the yo-yo won't jerk in any different direction unless you, of course, force it to. All right. So yeah, that's it for the centripetal force.